Alright, we got it. We have equal opposite polarity pulses created during the off time. Here we have our pulse frequency input, only 16% duty cycle. This is at 1.4 kilohertz, but you can see during that pulse off time we have a quick snap, but then a polarity pulse being generated there. I'm going to scoot this guy over a little bit and zoom in a little further, and you can see we do have a kind of negative build up there. You can see how the blue and green kind of separate into a pulse and come back, but that's being done many times a second. And that's essentially what we are going for. Even though they're not, really looking exactly the same, I want to show you how I came to this waveform right here. Really quick, I'm going to show you here. We're going to max this guy out at as high as we can, 32 volts. We have 91 volts across the cell right now, and if we increase the frequency, which I will do now, we can get this puppy all the way up to about 120 volts. It's even getting higher than that. Yeah, we're about 120 volts max there. So if we pause that there, so you can see 2.8 amps consumed at 32 volts. We got 119 volts across the cell, and cells producing accordingly for about that voltage level. We're gonna kick this puppy off here. Take a look at this once we get up to that frequency. This is our 0 point line right here, 0 volts right there. So we essentially have built up in the cell a spike and then collapse. We do have, a good amount of voltage potential. As you can see, we had it up to 120 volts. Now to the meat here, hold on. So through this transformer, as per one of our very old original transformers we're able to get high voltage out of, we have on the inside of here, that inductor, we have 2 coils bifilar wound, so essentially 4 wires. And here's the interesting thing about this. This one here on the positive end, you could say, is bifilar. We have one of these twisted together from one of the coils from here to the other coil to there to make it a bifilar actually wound. Essentially that would be the center tap of it. So that inductor here is bifilar wound. This inductor here is just dual wound, which means there's no center tap. It's just both wires coming out to the positive and then both wires coming out to the negative. Whereas opposed to this one, it's just one wire respectively with the 2 wires, the bifilar, coupled together. So bifilar, dual wound. That is the only difference. So by adjusting essentially the inductance on the secondary inductor, secondary choke, we can get the desired equal opposite polarity pulses. In Stan's patents, he talks about the secondary inductor being a variable inductor, and that is exactly it. That inductor needs to be variable in order to balance that positive or negative charge right at the cell. So that is my findings for early this morning, and let's take a look at that waveform one more time. There it is. It was really very much more distinct at lower frequencies, but we get the highest voltage output. That was at 5.8 kilohertz, still at 16% duty cycle. Let's switch this puppy on one more time. There we go, 120 volts at the cell. We're going to adjust that duty pulse just a little bit. We're going to increase it. Okay, we're getting up to 120.2 volts, and that's about the maxed out at 20% duty cycle. That puts us up to 3.5 amps at 29 volts. And if we go max out all the way, we can get that cell up to 120 volts. See if we can adjust that frequency a little bit more. Nope, that's going down. Let's see if we can get a little bit higher. Nope, that was about the sweet spot. Still only about 100 milliamps through that cell. Cell's producing accordingly, but again, nothing spectacular. There's our bubbler, just kind of barely bubbling. So, yeah, that is all.
This is Stan's Revenge.